So, what is actually the future of our universe? This image here is sort of a theoretical of what the entire observable universe could look like. So, from our current research, the universe is expanding at a rate which is quicker every year. So, it can be formed by a differential equation like this, where dv dt equals kv to the n plus 1, where n plus 1 is a constant, but it's changing every year. And this relationship, that the rate of change of the volume over time is ever increasing, is known as Hubble's law. So if you think of it like an inflating ball, points on the surface of the sphere will have a greater distance between them the more the ball is inflated. So if you can imagine, I'll just draw a simple basketball up here, for instance. If we have, say, a sort of a square here, these points, the bits that are marked X, as the ball increases, this area is actually going to increase and those points will diverge. So this could actually imply that the rate of change of volume over time is actually proportional to the surface area of a sphere, and then again the volume of the sphere. So it's actually, that should have been 4/3 pi r cubed, because that's surface area, so 4/3 cubed, my apologies. It's nothing to do with surface area, but it could be due to surface area. And where ours is the sort of radius of our universe, and t lengths of time after inflation. So t tends to be in years. However, Hubble's law does actually have a bit of limitations. One of them is actually the fact that our universe isn't spherical, so it's obviously not increasing at the same rate everywhere. But here's a couple more ones. So in the 1990s, we actually developed stronger technology to gauge the expansion of the universe. We have found these things in the smaller redshifts, which is the shift in the color of stars as they move towards or away from us. So this actually implies that the universe is actually slightly slowing down its expansion, not by much, but it is indeed slowing down rather than speeding up. But it is going so fast, we can never, get to the edge of the universe and break everything, for instance. So Hubble's law actually never accounted for this possibility, and it's only taken to a small degree of legitimacy. So what we can say is that instead of a regular differential equation, so dv by dt equals kv, we can write it in terms of a second order differential equation like a damped simple harmonic oscillation, as we discussed back in chapter 10, in the form ax double dot plus mu x dot plus omega squared x equals 0, where mu is greater than 2 omega square root of a, since you're on a steady decline. So this is to deal with types of damping, which I forget if we discussed, but if we did, that's great. If you didn't, well, there's a couple of videos on overdamping, critical damping, underdamping. This is overdamping because things are on a steady decline. So normally, if I just draw a graph, well, I'll draw two graphs here. So the original Hubble's law said that the growth of the universe was linear. No, it wasn't. That's the other one. That it was increasing every year, so it was actually quadratic, or some sort of polynomial. But that's the original. But what's actually happening is like this. So that it peaked here, roughly sort of after inflation. But it will still keep increasing, but it won't be increasing as much anymore. So that's really why Hubble's law is accepted per se, but shouldn't be taken as ironclad for the rest of the hundreds of billions of years that this universe will be around for.